Okay, so this is the review for Chapter 7, our first chapter in trigonometry. And I've gone through this review and added animations, trying to make this all just as clear as possible for everybody. This is the most important material that you have covered in mathematics throughout your K through 12 education. This is the door to calculus right here. So take great notes. Ask questions. If you run into a wall, give me an email and I'll get back to you as soon as I can. You make sure you have every one of these concepts down. All right. It leads to so much more very advanced trigonometry, which is right on the horizon. So I'm sorry I didn't have room for the title on this slide, but apparently there's a whole bunch on this slide. So we'll blow it up big so you can see the questions. Anyway, 1A. Convert 270 degrees to radians and then give the answer in terms of pi. All right, so conversions. It's really easy to convert from degrees to radians or from radians to degrees. So what we're going to do is we're going to take this 270 degrees and we're going to multiply it by a fraction that is equivalent to 1. And you guys know now, let me see, we want an answer in terms of pi and we're going radians. So I'm going to put pi in my numerator. And what is the equivalent to pi in degrees? That would be 180 degrees. And pi over 180 degrees is 1, so we are multiplying this 270 degrees by 1 right here. But now watch what happens. Do you see your units of degrees? They just cancel out now. And they want the answer in terms of pi. So I could write this 270 pi over 180. But I think we can simplify 270 over 180. That would be 27 over 18 or 3 over 2. And if you're struggling with simplifying, you can do it on your calculator too. I think I'll show you that on the next one, which is a little more complicated. So now we're going to convert 192 degrees to radians. So same thing, 192 degrees to radians. I need to multiply it by a fraction, which is equivalent to 1. And we're going to write that fraction as, I want my answer in radians, so pi in my numerator and 180 degrees in my denominator again. All right, and once again, the degrees cancel and they want the answer in terms of pi, so this would be 192 pi divided by 180, but I'm betting we can simplify 192 divided by 180. And this one's a little more complicated. It's a test. I'm stressed for time and stuff, so I would probably just go ahead and punch this out on my calculator. So look what I did. Math fraction on my calculator. So if you guys hit math fraction, you're going to get this 192 divided 180, and your calculator will give this to you as a decimal. That is a repeating decimal, 1.06 with the 6 repeating. And then here's what comes up when you hit math fraction. Answer fraction. Okay, so I hit enter after that and I get 16 over 15. So guess what? 192 over 180 reduces to 16 over 15. And there's your answer to 1B right there. All right, get really good at this math fraction because it's great to be able to simplify fractions, and you've got a great calculator that will do that for you. Okay, part B. Oh, now we're converting the other way. Note, they give you an angle in radians, 5 pi over 3, and they want to convert this to degrees. So it's the same setup. We take our angle in radians, 5 pi over 3, and we're going to multiply it by a fraction that is equivalent to 1. But the fraction, this time, since we want our answers in degrees, we're going to put the 180 degrees in our numerator, and then the pi radians in our divisor. Now, this one, your factors of pi would cancel out, all right? And then you're just going to go, well, cancel those pi's right there. And I think we can do this one without our calculator. 3 goes into 180 60 times, and 60 times 5 would be 300. So that's 300 degrees right there. Okay, now 2b. convert 2.5 radians to degrees. All right, so 2.5 radians times the same unit multiplier, 180 degrees over pi. All right, now this one, and notice there's not a pi in my original angle, it's just 2.5 radians, and that's why they said give the answer to the nearest 10 minutes or tenth of a degree. So I'm going to punch this out on my calculator, and my answer will be in degrees. So there's my degree symbol right there. So what's 2.5 times 180 divided by pi on my calculator? Tenth of a degree, it would be 143.2, and the rest of this decimal is 39448 if you're interested. But they want the answer as 143.2 degrees. All right. Now notice too, they said give the answer to the nearest 10 minutes or tenth of a degree. So if you just give me 143.2 degrees as your final answer, I have to give you full credit. That or right there, you do not have to do both. All right, but this reviews a learning experience, so let's practice converting 143.2 degrees to degrees and minutes. So to the nearest 10 minutes, well, 143.2 degrees. That would be 143 degrees plus, and then 0.2 of 1 degree, which I'm going to go 0.2 of, and then I'm going to go, how many minutes are in 1 degree? That would be 60 minutes. Right there. All right, now let's simplify that. So that equals 143 degrees. And then what is 0.2 of 60? I'm just going to go and punch that out. All right, so I'm going to go 0.2 times 60, and I'm getting 12 minutes. All right. Now that's very accurate right there, 143 degrees and 12 minutes. But notice they said to the nearest 10 minutes, so we better round this appropriately. So that is approximately 143 degrees, and then 12 minutes rounded to the nearest 10 minutes would be in 10 minutes. That's interesting how they asked us to round that to the nearest 10 minutes. Anyway, if I were taking this test, I would have written 143.2 degrees, and I would have moved on to number 3. Okay, now, number 3, speaking of number 3, find two coterminal angles, one positive and one negative. Part A, negative 200 degrees. So let's visualize negative 200 degrees on our circle right here. So let me see, negative means I'm going in a clockwise direction, and remember my initial ray is the positive x-axis, so let's go clockwise. Well, there'd be negative 90, negative 180, and so negative 200 would be out here in quadrant 2, something like that right there, negative 200 degrees. Now watch how easy this is. All right, I need two coterminal angles that are equivalent to negative 200 degrees. That means they're angles with a different measure, but they have the same terminal ray right here. So the easiest way to do that would be to add or subtract, I should say and subtract negative 200 to 360 from that negative 200. So I'm going to go minus 360 degrees and then plus 360 degrees. Well, if I take negative 200 degrees and I subtract 360 degrees from that, that means I'm at negative 200 and then one more revolution. That would be negative what? Well, negative 200 minus 360, that'd be negative 560 degrees. So my negative solution, negative 560 degrees. Now let's add 360. So 360 degrees minus 200 degrees, that would be 160 degrees. Well, that's pretty easy. Now, let's go ahead and let's visualize 313.2 degrees. And this is not going to be perfect, you guys, but this is a positive angle, so I'm going to start on the positive x-axis, and I'm going to rotate clockwise, 90, 180, 270, one revolution would be 360, I need 313, so that's going to be here in quadrant 4 somewhere. And it doesn't have to be perfect, you guys. There's my approximation right there of 313.2 degrees. And now I'm going to do the same thing. I'm going to add 360 to that, and I'm going to subtract 360. Remember, if I add 360, that's just one more revolution. Okay, and if I subtract 360, I'm here, and I'm going now this way, and I'm getting there the same way. So I'm going to do this with the 0.2. I'm just going to do it right on my calculator. Watch this. All right, comma. So I did 313.2 minus 360, and I got negative 46.8 degrees. So this negative angle right here is exactly negative 46.8 degrees. All right, and then when I added 360, I got 313.2 plus 360, and I got 673.2 degrees. So the 313.2 plus one more revolution is 673.2. There you go. Now, 5 pi over 6, we're now in radians. All right, so let's clear the degrees from our diagram right here, and let's think about 5 pi over 6. Well, let me see. 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. I'm visualizing it right here, and this is positive, so this angle is going to come around to about right there for a terminal ray. Look at that, 5 pi over 6. Now, because I'm in radians, instead of doing plus or minus 360 degrees, we're going to do plus or minus 2 pi. That's one revolution in radians, 2 pi. So 5 pi over 6 minus 2 pi. All right, well, let's do it like this. Let's try it in our head first and see how we do. All right, so if I go 5 pi over 6 minus 2 pi, let's take the pi's out of the mix and go 5 over 6 minus 2. Well, that would be 5 over 6 minus 12 over 6, and that's negative 7 over 6. Check it out. I did it on the calculator too right there. Negative 7 over 6, so negative 7 pi over 6. Okay, and I did the adding 2 pi, and I took the pi's out of the mix again, so I went 5 over 6 plus 2, which I'm going to think of as what, 12 over 6? And isn't that 17 over 6? Yes, look at that right there. So my answer, my positive answer, would be 17 pi over 6. Wow. Don't make this more complicated than it is. And if you feel more comfortable on your calculator, use your calculator. All right. This is about understanding coterminal angles. It's not about the arithmetic. All right. Now, the last one is the most complicated because we have 142 degrees and 10 minutes. All right, now watch what I do here. Oh, by the way, there's my visualization, 142 degrees and 10 minutes. That's an approximation, not perfect. All right, and again, what? We're going to have to plus or minus 360 again. All right, so 142 degrees and 10 minutes. Well, I'm going to subtract 360. Right there, and I'm going to ignore the minutes for just a second. So 142 minus 360, what's that going to be? That's going to be negative 218. All right, now think about this though. There were 10 minutes right here that I have not accounted for. All right, so I better go negative 218 degrees, and I still have those 10 minutes plus the 10 minutes right there. All right, now let's simplify this. Equals, all right, so negative 218 degrees, but if I add 10 minutes, I'm going to be at negative 217 degrees and 50 minutes. Negative 217 degrees and 50 minutes. Oh, that's so cool. All right, now let's add 360. Now that's going to be a little easier here because if I add 360, I'm just going 142 plus 360. And where'd that, oh, I checked this one, didn't I? Okay, hang on here a second. 359. What's this 217? Oh, plus 142. I get it. So I'm going the 217. I'm just checking my work here. Plus the 142, and I got 359. And then the 10 and the 50 gives me my other degree for 1 revolution. Now let's get to the problem I'm on, though, right here. And I went 142 degrees plus 360 degrees, and I got 502 degrees. But now don't forget, you also have those 10 minutes. 10 minutes right there. And there you go. All right. So again, this is just arithmetic. So think about your answers and don't make an arithmetic mistake. You'll be fine. If you're comfortable with your calculator, do it. If you're comfortable doing this in your head, do that. Okay? Thank you. All right. Number 4. A sector of a circle has radius 5 centimeters and central angle 48 degrees. Find its approximate arc length and area. Okay, great time for a diagram right now so we can visualize everything. And the radius is 5 centimeters, so let's put a 5 on one of the radii of this circle. And then the central angle is 48 degrees, so this angle right here would have to be 48 degrees. Now, we need to find the approximate arc length, and we use an S for the arc length of a circle. And then after that, we will find the area, for which we will use a K for area, by the way. All right, so when theta is in degrees, I take a simple fraction of my total circumference of the circle. So theta in degrees implies use the ratio, and the ratio is going to be your central angle over 1 complete revolution, 360 degrees. And I have your formulas for both finding the sector and the area, or the arc length and the area of a circle, based upon if your central angle is in degrees or in radians. So we're in degrees, so we're going to be using these two formulas right here. Okay, so first off, what is the ratio I'm using to multiply my circumference by? Central angle over 360. Okay, so let's just take this and then multiply by circumference. So that means this sector is, what's the central angle? 48 degrees. Over 1 complete revolution, 360 degrees. And I didn't use degrees because they would just cancel out there anyway. So I'm just 48 over 360 times the circumference of a circle. Wow, I use an X for times. That's old school. And what's the circumference of a circle? It is 2 times pi times r. And by the way, you see that right there in your formula too, just in case you forgot it. So 2 times pi, and what's the radius of my circle? It's a 5. Now, they asked us to approximate this, which means we're going to punch this all out, including the pi, and what we round to, that's up to us. They didn't tell us what to do. So as long as we round correctly, it doesn't matter if we round to the nearest whole number, to the nearest tenth, to the nearest 100th, to the nearest thousandth. Personally, I usually like to round to the nearest 100th in pre-calculus, but I'll mix it up on you guys time again here. So let's punch this out very carefully. So I'm going to go 48 divided by 360 times 2 second pi times the 5. All right, double check your calculator, make sure it's all in correctly. And to the nearest 100th, I'm getting a 4.19. And now, do I know my unit here? Because remember, this arc length, that S is a distance. What is the actual distance right there? And since the radius was given in centimeters, then this distance right here is approximately 4.19 centimeters. All right, now area, which we use a K for the area of a sector of a circle. So K equals, and now we're still, our central angle is in degrees, so we're going to go our 48 central angle over 360, but now this fraction times the area of the entire circle times, I use an X again, and you guys know area of a circle, pi r squared. There's a little reminder there, and by the way, it's in your formulas down here too. So pi times the radius squared, and the radius is still 5, And again, we're going to approximate this, so we're going to punch all that out, including the pi, and decide what we want to round to. Okay, so let's see. 48 divided by 360 times second pi times the 5 squared. I'm just going to put a 25 in if you guys don't mind. 48 divided by 360 times pi times 25. And I'm getting a 10.471975551. What do I want to round to this time? Oh, I am mixing it up. I'm going to round this one to the nearest 10. So can I go 10.5 there? 10.5. And since my units are in centimeters and this is area, this would be square centimeters. And there's number 4. Great problem. Okay, the moon is approximately 4 times 10 to the 5th kilometers from Earth. And its apparent size is approximately 0.0087 radians. Remember our cool diagram for apparent size? Here it is right here. All right, that apparent size is this angle theta right there. Okay, so let's use this as a diagram to come up with the moon's approximate diameter. And I'll tell you what, I'm going to use the part of the diagram that represents a sector of a very big circle. Okay, so here's my sector of a much larger circle that we do not have room for. But this is that little piece of the pie right there. And now all we have to do is put in what we know. And so apparent size is 0.0087. That's this angle right here. Oh, what did I see first? And the moon is approximately 4 times 10 to the 5th kilometers from Earth. So that's the distance from my eyeball to that edge of the moon right there. 4 times 10 to the 5th. And then my apparent size is at 0.0087. All right, cool. Now, what's the moon's approximate diameter? Well, you guys remember that we can use this arc length right there to approximate the diameter of the moon. All right, so that arc length S, and remember, diameter is approximately arc length S right here. So let's go to work here. So do you remember how to find arc length if your angle is in radians? Real simple formula right here. If theta is in radians, arc length is theta times r, the radius of your sector. So S is going to be, and my theta is that 0.0087. There it is, times my radius of the sector, or the big circle that we cannot see all of, and that's just the 4 times 10 to the 5th. Okay, and now we're approximating this. And what is the moon's approximate diameter? Well, we're just going to round whatever we get for this sector right here. We're going to round it to the nearest whole number, because this is a real rough estimate right here. All right, so let's just punch it out very carefully again. 0.0087 parenthesis 4 times 10 to the 5th power, close my parenthesis. And then you double check your calculator and make sure everything's in there correctly. 0.0087 parenthesis 4 times 10 to the 5th. I like it. And I'm getting 3,480 exactly. Are you kidding me? Let me double check this. 0.0087 times 4 times 10 to the 5th. Wow. So guess what? The diameter of the moon, I don't even need this approximation right here. It is 3,480. And what would my units be in right there? 3,480 kilometers. There you have it. Okay. Again, the arc length. I was so surprised when I did that 0.0087 times 4 times 10 to the 5th, and I actually got a whole number right there. Wow. Okay, anyway, on to number 6. Okay, now here we go. Now we're getting big time. We have our typical diagram of a terminal ray on a circle. Okay, and they're asking us, just giving this, let's find sine of theta and cosine of theta. All right, well, let's kind of complete this diagram, because you know what I really want? If I have a second quadrant terminal ray to this positive angle right here, theta, I would like to put a second quadrant right triangle into this picture and put my dimensions of the triangle. So algebraic definitions of our trig functions. Here's what we're using right here. Okay, sine of theta is y over r, and so on. And there's all 6 of them right there. Our sine, cosine, and tangent, and then our reciprocal functions, cosine of theta, secant of theta, and cotangent of theta. Now, let's complete the diagram of our first quadrant right triangle. There we go, right there. Now, with these points, I can put the legs of my triangle into the diagram. The x-coordinate is -1. That means this lower leg right here would be -1 because x is negative. And then this leg would have to be that y-coordinate right there, which is going to be +1. Now, you can find the radius of the circle with Pythagorean theorem if you'd like, but if you've got your special right triangles down, you can be much more efficient, because this is a 45, 45, 90 triangle, and you guys from geometry should remember that the ratios of the sides of a special right triangle that's 45, 45, 90 would be 1 to 1 to root 2. And look at 1, 1, that's got to be root 2. That negative doesn't matter here. We're talking magnitude. So the radius of this circle is the square root of 2. And don't sweat it if you don't remember your special right triangles. You could have got that just as easily with Pythagorean theorem. All right? But now, with this diagram, I have everything I need. I have an x, I have a y, and I have a radius. And the algebraic definitions of all of my trig functions are in terms of x and y and radius. All right, so sine of theta equals, and sine of theta is what? It is y over r. See it right there, y. Oh, I thought I put the general. I guess I have it here. So y, and what's the y coordinate of my point? It's a 1. What's the radius of the circle? It is root 2. And now for full credit, we have to rationalize this denominator right here. So I'm going to multiply the top and the bottom by root 2. 1 times root 2 is root 2. And root 2 times root 2 will give me a 2. So sine of theta is root 2 over 2. Now cosine of theta. Well, cosine of theta is x over r. And you see that right there. So what's the x-coordinate of my point right there? It is a -1. Over, and the radius is still the square root of 2, and we've got to rationalize this divisor right here, so we're going to multiply numerator and denominator by root 2 to get a negative root 2 over 2. Now make sure you see that. -1 times the square root of 2 is negative root 2, and the square root of 2 times the square root of 2 is 2. All right, rationalizing the denominator like you did in algebra. Okay, that's number 6. Oh, there's more to it. Okay, must be a part B. All right, again, I've got this diagram of a circle with a terminal ray in quadrant 3. And you know I'm going to do a quadrant 3 right triangle, and I'm going to use my algebraic definitions of all of my trig functions. So there's my algebraic definitions again, and let's complete the triangle right here. So let's look at our dimensions right here. So the x is -1. That means this short leg right here has a length of -1, including direction. Okay, now the y is negative root 3. That means this distance right here would be negative root 3. And now, 1 to root 3, that sounds familiar. Guess what? It's another special right triangle. This is a 30, 60, 90 right triangle right there. Okay, and the ratios of any 30, 60, 90 right triangle would be 1 to root 3 to 2. And again, if you don't remember that, you can find the radius of the circle just as easily using Pythagorean theorem. This does make us a little more efficiently, especially here, because I have, remember, direction doesn't matter. -1, -√3. That means the radius of this circle, or the hypotenuse of this quadrant 3 right triangle, would have to be a 2. And there you go. That's everything you need. Find sine and cosine. Okay, one more time. Sine of theta is y over r. There it is right there. So y here would be -√3. All right, and the radius is 2. -√3 over 2. I don't even have to simplify that one. The radical was already on the top. Now cosine of theta. Well, cosine is x over r. And my x is -1 over the radius 2, -1/2. And there you go. 6 part B. All right, hey, a part C. Oh, and this is a quadrantal angle right there. That angle theta is 90 degrees, or you could think of it as pi over 2, whichever you like right here. All right, and let's find sine and cosine. Okay, well, again, here's my algebraic definitions, real simple. And you know, with quadrantal angles, you really usually don't even need to look at that, but that's there just in case. All right, quadrantal angle, okay, 90 degrees or pi over 2 if you'd like. All right, and so what do I know? Well, this is the unit circle right there, so that's 1. So the radius is 1, the x-coordinate is 0, and the y-coordinate is 1, just in case you want to use these. I'm more visual, so I'm going to go sine of 90 degrees. I know sine measures vertical distance. So what's the vertical distance at 90 degrees? That's exactly 1 unit. By the way, if you use the y over r, y is 1, the radius is 1, and 1 divided by 1 is 1. Now cosine of 90 is even easier to me, because cosine is measuring a horizontal distance. There's no horizontal distance here, so that's 0. But if you want to do this, you could. All right, and that's going to be x over r. Well, x is 0, r is 1, 0 divided by 1 is 0. So there you go. Sine of 90 degrees is 1 unit. Cosine of 90 degrees would be 0 units. All right, number 7. Complete each statement with less than, greater than, or equal to. Well, this is going to be fun. And to help you, I would draw a diagram so you can visualize these things here. So here we go, my typical circle right here. Now, I'm going to estimate a 60-degree angle, so a terminal ray at 60 degrees. All right, and this won't be perfect. I'm not going to do this to scale because I want to exaggerate a few things. So not to scale here, because I need now a 65-degree terminal ray, and I'm going to exaggerate that a little bit. There you go, right there. Now remember what we were just talking about on the previous slide, how sine measures a vertical distance from the x-axis, and cosine measures a horizontal distance from the y-axis. Okay, so think about this here now. All right, the 60 degrees, look at this vertical distance right there, and the 65 degrees, that vertical distance is a little more. So sine of 60 would have to be less than sine of 65. And again, I'm just visualizing these vertical distances right here. Okay, now cosine is the horizontal distances. So cosine of 65 is going to be shorter than cosine of 60. So which one do they do first? Cosine of 60 degrees has to be greater than cosine of 65 degrees. And again, there is my horizontal distance for cosine of 60 degrees. And there's the horizontal distance for cosine of 65 degrees right there. Cosine of 60 is greater than cosine of 65. There you go. Now, sine of 20 degrees and then sine of 160 degrees. So let's do a terminal ray for 20 degrees. And then do a terminal ray for 160 degrees. Oh, look at that. All right, isn't 20 degrees a reference angle for 160 degrees? Yes, it is. And we're talking sine of those two angles right there, which measures this vertical distance. And those two vertical distances would be equivalent. So sine of 20 degrees equals sine of 160 degrees. What, did I call that 60 earlier? I hope not. Anyway, last one right here. Cosine of 184 degrees, how does that compare to cosine of 185 degrees? Well, 184 degrees, a little beyond 180, about right there. And again, not to scale because those are really close. All right, I'm going to exaggerate the 185. There we go. Yeah, I exaggerated that quite a bit, didn't I? But that's so you guys could clearly see. Cosine is measuring this vertical distance or horizontal distance, but remember that's negative right here, right? So this negative distance represents the cosine of 184 degrees, and then this negative distance represents the cosine of 185 degrees right there. All right, well, it looks to me like cosine of 184 is a little farther to the left than cosine of 185. So cosine of 184 would have to be less than cosine of 185. And again, think about it because you're going in a negative direction, but this is going to be a less than. All right, number 8 in the books. Hope you guys are doing well. Number 8. What, did I have 2 number 8s there? Oh, that was number 7. I tell you, I must be tired or something. I'm working too hard. All right, here's number 8. Give an exact value for each expression in simplest radical form. Now, the key thing here is exact value means I can't just punch these out on a calculator. Well, my calculator might give me an exact answer for cosine of negative 90 degrees, but that's it. All right, so let's think about exact values. We want to use our quadrant 1 reference angles. And there's your diagram right there. I hope you have this memorized and you don't have to bring this up every time. All right, but now you think to yourself, where is 5 pi over 4? Well, 1 pi over 4, 2 pi over 4, 3 pi over 4, 5 pi over 4? That's this terminal ray right here in quadrant 3. Oh, and we're going to use symmetry. Right on. So anyway, there's my 5 pi over 4 right there. Now, what is the reference angle for 5 pi over 4? It would be pi over 4 right here. All right, so let's put that terminal ray in quadrant 1 for our reference angle right there. Now you think about this. Okay, sine of 5 pi over 4. Well, sine of, what are we looking for? 5 pi over 4? I don't know what that is right off the bat, but I do know that sine of pi over 4 is, and this vertical distance right there would be root 2 over 2, which I see right here, root 2 over 2, that y. Okay, now that implies sine of 5 pi over 4 would be, well, now we're talking a vertical distance right here, which is the opposite of my root 2 over 2. So this is going to be negative root 2 over 2. Okay, cool. So let's put our answer over here. Sine of 5 pi over 4, we got a negative root 2 over 2. Okay, let's do cosine of negative 90 degrees. So let's picture the terminal ray for negative 90 degrees. Here it is right here. And you know, for these quadrantal angles, again, you guys, I don't use much because I know sine measures vertical distance and cosine measures horizontal distance. So what's the horizontal distance for the terminal ray at negative 90 degrees? There is no change horizontally, so that would have to be a 0. Okay, sine of 150 degrees. Well, 150 would be over here in quadrant 2. Okay, and the reference angle for 150 degrees would be 30 degrees, which will be right there in quadrant 1. And now let's use sine of our reference angle. So we're going to go sine of our reference angle to 150 degrees would be 30 degrees. And what does sine of 30 degrees equal? What is this vertical distance right here exactly? That's right, it's 1/2. And you see it right here in your first quadrant reference angles, root 1 over 2. That's a 1/2. So that implies sine of 150 degrees. Well, we're going to have the same vertical distance again, so that has to be 1/2. So the answer to C, 1/2. Okay, last one. Cosine of 11 pi over 6. That's a lot of pi over 6's. Isn't one complete revolution 12 pi over 6? So we're going to be pi over 6 radians short of one complete revolution. So that's going to be like right here. There you go. And of course the reference angle to this is this, what we used for what, 30 degrees a little bit ago, but now think of that as pi over 6. Okay, so here we go. Cosine of, well, the reference angle for 11 pi over 6 would be a pi over 6. And cosine of pi over 6, well, I'm talking now the horizontal distance of this triangle right here, and that's going to be that root 3 over 2. And by the way, you see that right there with that x-coordinate, root 3 over 2. All right, so that implies cosine of 11 pi over 6, which is this terminal ray right here. And wouldn't that be the same horizontal distance there? So that also has to be a root 3 over 2. So the answer to D, root 3 over 2. All right, that's cool stuff. Number 9. Give the exact value of each expression or state that the value is undefined. So again, exact values, we can't just punch these out on our calculator. So, tangent of 135 degrees. Well, I don't know exactly what tangent of 135 degrees is, but I do have my reciprocal relationships. And I do know that tangent is 1 over cotangent, which probably isn't going to help me here, but I also know it's sine over cosine. So there we go. Tangent of theta equals sine of theta over cosine of theta. So let's write this tangent of 135 degrees as sine of 135 degrees over cosine of 135 degrees. And now we can get each of those and answer this question. So what is sine of 135 degrees? All right, well, we better visualize that and then get a reference angle. So let's think about this. 135 degrees. Wouldn't that be right there? Oh, yeah. And isn't the reference angle for 135 degrees going to be 45 degrees? Right there. And I know sine of 45 degrees is this distance right here, root 2 over 2 from my first quadrant reference angles. So this right here, this point has to be, the x is root 2 over 2. And again, look, I'm just using my diagram again here, the root 2 over 2. And the y is root 2 over 2. So here we have it now. All right. So sine of 135 degrees would be equivalent to this root 2 over 2 because this is the same vertical distance right there. All right. And again, I'm doing this thing right here. This point is xy, makes this point the opposite of xy. Root 2 over 2. And now cosine of 135 degrees is, well, cosine of 45 degrees would be root 2 over 2. So cosine of 135 degrees would be this horizontal distance, which is negative root 2 over 2. And root 2 over 2 over negative root 2 over 2 equals -1. Nice. I'm sorry, my dog is barking. I hope it's not bothering you guys. Part B. Okay, cotangent. Well, again, I don't know cotangent of 2 pi over 3, but I can sure diagram here. All right, so cotangent is going to be what? 1 over tangent, which probably won't help me as much as cosine over sine. Cotangent of theta is cosine of theta over sine of theta. So cosine of 2 pi over 3 over sine of 2 pi over 3. Now we can find both of those to answer this question. So 2 pi over 3. Well, pi over 3, 2 pi over 3 would be about right there. Nice. And the reference angle for 2 pi over 3 is that pi over 3 over here in quadrant 1, right? And that is this angle right here where I see my x and y coordinate. So let's put the coordinates of this endpoint right here, that terminal point. And the x right there would have to be root 1 over 2, or 1/2. And the y right there, that vertical distance, would be root 3 over 2. There you go. So here we go. Cosine of 2 pi over 3. Well, that's that horizontal distance right there. 1/2 on the reference angle. So over here, that's going to be a 1/2, but it's going to have to be negative. Negative 1/2. Sine of 2 pi over 3. This vertical distance is root 3 over 2. We have the same vertical distance over here on the 2 pi over 3. So that's also going to be root 3 over 2. And now you just simplify this. Equals, well, think about this a second. Your 2's would cancel, and you have a negative 1 over root 3. Negative 1 over root 3. Again, those divisors just canceled. And now we've got to rationalize our denominator. So equals, boom, negative, and then we've got to multiply the numerator by root 3 to get a root 3. And if I multiply the denominator by root 3 times root 3 is 3. There you go. Now, secant of negative 60 degrees. Well, secant is 1 over cosine. So 1 over cosine of negative 60 degrees. Okay, well, here's the terminal ray for 60 degrees. Negative 60 degrees is going to be down here. There you go. All right, now think about this. All right, let's go equals. Well, I know I have a 1 in my numerator, so let's start with that. And now think about cosine of negative 60 degrees. Well, if cosine of 60 degrees is 1/2, wouldn't cosine of negative 60 degrees also have to be 1/2? 1/2, and 1 over 1/2 would be 2. Whew, that was fun. And then, oh, a quadrantal angle, I like that. Cosecant of negative pi. Well, cosecant is 1 over sine, so that's going to become, and then where is it? Right here. Cosecant of theta is 1 over sine of theta. So that's going to be 1 over sine of negative pi. Well, let's look at negative pi, the terminal ray. Here it is right here. All right. And doesn't sine measure vertical distance? I've got no vertical distance here, just horizontal. So that's a 0. What's 1 over 0? That's right, undefined. And there you have number 9. Wow, a lot of stuff going on there. Okay, number 10. If tangent of x equals negative 1/3, where pi over 2 is less than x and x is less than pi, so they're using x for their angle here. And that's okay, but it might confuse a few people. Find the values of the other 5 trigonometric functions. Ooh, so here's the other 5 right there. Now, let's draw our typical picture. The diagram, a circle centered at the origin. Okay, now we're from pi over 2 to pi, so our terminal ray has to be here in quadrant 2. So I'm going to do a quadrant 2 terminal ray. It won't be perfect to scale, but that's okay. All right, and now I'm going to do that quadrant 2 right triangle so I can put my dimensions of the triangle in. So here we go. Here is my quadrant 2 right triangle right there. And now, let's see. Let's think about the coordinates of this point. All right. Well, isn't tangent y over x? All right. So we can do it here, and I'm using my algebraic definitions. I'm sure I brought those up here somewhere. I guess I didn't yet, did I? Okay. All right. Oh, I see what I'm doing here. I want to make sure you guys understand now. This angle is x right there. Okay, so I prefer a theta, but x works. But don't confuse the angle x with the x coordinate of this point right here. They are very different. All right, so here are my algebraic definitions. Tangent, again, is y over x. Okay, so this x is an angle, but that x right there, we're talking the x coordinate of this point right here. Okay, now how is this going to work? Okay, well, tangent is y over x. That means that this vertical distance would have to be a 1, And then the horizontal distance is negative, and that's going to be the negative 3. So do you see that? Okay, 1 over negative 3, y over x, negative 1/3. So let's put those coordinates in here. The x is negative 3, the y is a 1, and now if I had this hypotenuse to my second quadrant right triangle, or the radius of that circle, I'd have everything I need to answer all these questions. All right, so, well, that's not a special right triangle, so we're going to have to use Pythagorean theorem. Wow, been a while since we had to do that. So let's square the negative 3, and I'm going x squared plus y squared equals r squared. Negative 3 squared would be 9. 1 squared would be a 1. And that has to equal the radius of this circle squared, r squared. And 9 plus 1 is 10. So if r squared equals 10, r would have to equal the square root of 10. Now, with that diagram, with my second quadrant right triangle labeled with dimensions, and my algebraic definitions of all 6 trig functions, I have the answer to all of these right now. So that's all I need right there. So let's go to work. So sine. Well, sine is what? Sine is y over r. And y would be, well, what's my y coordinate? It's a 1 right there, right? R, what's my radius? It's root 10. Okay, now we can't leave our answer like that. We have to rationalize our divisor. So that's going to equal, and let's multiply numerator and denominator by root 10. So 1 times root 10 is root 10, and root 10 times root 10 would be a 10. There you go. Cosine x over r. What's my x coordinate? Negative 3. I put the negative out front. 3, you could have put it up top too. That doesn't matter. Over r is still root 10 equals. Now, let's rationalize this denominator. So I'm going to have to multiply the numerator by root 10. So that's negative 3 root 10. And then root 10 times root 10 is 10. Cosecant of x. All right. Well, this is kind of cool because now we start doing our reciprocals. And isn't cosecant the reciprocal of sine? Right there. All right. And you could do it over here and use the r over y if you want to. All right. But I like to do this. Since cosecant is the reciprocal of sine, and note sine was 1 over root 10, then cosecant would have to be root 10. Secant is the reciprocal of cosine. So if my original secant before I rationalized the divisor was negative 3 over root 10, what's the reciprocal of negative 3 over root 10? That would be negative 10 over root 3. Look how easy that is. And cotangent of x. Well, this is even easier because that one was given. Tangent is up there, and tangent is negative 1/3. Cotangent is the reciprocal of tangent. So what's the reciprocal of negative 1/3? Negative 3. Oh, those reciprocal functions. Easy. Okay. Number 11. Give the exact values of each expression. Man, they're asking us to do a lot of stuff without our calculator. Okay. Inverse tangent of root 3. All right. Now remember, what does this really mean? Inverse tangent means the angle whose tangent is root 3. And that means all I am looking for is that theta. That theta. Tangent of this theta is root 3. The angle whose tangent is root 3. So I need to know, when does tangent have an output of root 3? Wow. Remember our first quadrant diagram? We don't have any root 3's. We do have root 3 over 2. Let's see what we can do here. So now, isn't tangent sine over cosine? Tangent of theta, sine of theta over cosine of theta. So I'm going to rewrite this tangent of theta equals root 3 as sine of theta over cosine of theta. And that's going to have to equal root 3. But how can I make that happen? Well, root 3. Do you guys agree that root 3 could be root 3 over 1? Now let's look at our reference angles and make that happen. Well, I don't see a root 3 all by itself, but look at this pi over 3 right there. That angle right there. Okay? Root 3 over 2, and then root 1 over 2. So what if I did this? See this root 3? I'm going to write it as root 3 over 2. See the 1? I'm going to write that as 1 over 2. And that then is definitely this angle where sine is root 3 over 2 and cosine is 1/2. All right? So what is that angle? That implies that angle theta is, well, let's see, pi over 6, pi over 4. That's my pi over 3 right there. Isn't that cool? All right. Now cotangent of the angle whose sine is 1/2. So when does sine of theta equal 1/2? We're looking for that angle theta. Well, I know right here, sine has an output of 1/2. See this point right here? This vertical distance right there is 1/2, and that angle is pi over 6. So this is nothing more than cotangent of pi over 6. All right? And then I've got to do my reciprocal functions again. Cotangent of pi over 6, that's going to be my cosine of pi over 6 over sine of pi over 6. All right, and let's do that. So what is cosine of pi over 6? Well, here it is right here. This horizontal distance right there is that root 3 over 2. And that's my terminal ray for pi over 6. Root 3 over 2. And what's sine of that pi over 6? That would be the 1/2. And root 3 over 2, hey, that looks familiar. Over 1/2 equals 2's cancel. We got root 3 over 1, which I'm going to write as a root 3. Okay, now finally, this one looks more complicated, but guess what? See the inverse cosine? And isn't secant 1 over cosine? So let's do the reciprocal of this secant of inverse cosine of -3/5. 1 over. Now, what's the reciprocal of secant? It is cosine. Where am I at right there? Right there. So this becomes 1 over cosine of inverse cosine of -3/5. Now, why did I want to do that? Looks more complicated. Or does it? Because what is cosine of inverse cosine? Those are inverses. They just undo each other. There you go. And I'm left with 1 over -3/5. Well, 1 divided by -3 over 5. Let's just invert and multiply. That'd be -5 over 3. There you go. These are really cool problems. Okay. To obtain the inverse sine function, we restrict the domain of f of x equals sine of x to -pi over 2 is less than or equal to x, and x is less than or equal to pi over 2. Write a short explanation in which you discuss why this restriction is necessary. Well, in layman's term, for a function to have an inverse, doesn't it have to be 1-to-1? And sine is obviously not 1-to-1. All right, sine oscillates between -1 and 1 forever and ever and ever. It's periodic. So the restricted domain always has to have the first quadrant. Let me get that out of here for a second. Always has to have the first quadrant, which would be 0 to pi over 2. But then you want the largest interval of sine containing the first quadrant where sine is 1-to-1. So the restricted domain is the largest x interval containing quadrant 1 in which sine is 1-to-1. And here's a picture of sine. We did this graph earlier. And again, well, from -pi over 2, which is this x value right here, to 0, and then on to x equals pi over 2, that is the largest interval where sine is 1-to-1, but I contain quadrant 1 right here, the 0 to pi over 2. Oh man, that was the test, or the review I should say. Looks pretty similar to your test though. So that's it in a nutshell. Okay, you guys, I hope you enjoyed this. I was kind of tired today. I hope I didn't get loopy on you at all, and I hope I explained everything very, very well in this video. If you have any questions, drop me an email. I'll be happy to help you out. Okay? You guys get your notes set up, and you be ready for this exam. Everybody have a great day.